Okay, so far we have analyzed the motion of particles in coordinate systems which are known as Cartesian coordinate system. So we have done motions of particles in Cartesian coordinate systems. So without saying it explicitly that we are using Cartesian coordinate system, we were actually analyzing the motion of particles in the Cartesian coordinate systems, which are essentially nothing but coordinate systems where you have orthonormal axis, right? So you have x-axis, you have y-axis, you have z-axis, and you have unit vectors I hat, j hat, k hat pointing along those three directions, and you have particle moving along curved path, right? So you have particle p whose position vector was given by r. Let's say an r was given as a function of time I hat plus yt, j hat, and zt, k hat. So this is actually a three-dimensional motion. Okay, so if I wanted to get the velocity, I took the differentiation d over dt of r, and that was basically nothing but d over dt of this term over here, right? So x I hat plus y j hat plus z k hat, and I have dropped the time over here because we are assuming that x, y, and z are actually function of time only, right? So if I differentiate this, what do I get? I get d over dt of x, so dx over dt I hat, plus we are also taking the derivative of I hat, right? Because I hat is a vector, unit vector. So what about its derivative? So we can take that as well, d over dt of I hat, and that is just for this term, okay? Then for the next term, we have d over dt of y I j hat plus y times d over dt of j hat. Okay, and let's just restrict ourselves to 2D, which means we're going to just disregard the z component. Okay, we're not really doing 3D motion over here, but if we are doing it, it won't be a big deal. We will just extend this to third dimension as well. Okay, so what is this quantity d over dt of I hat and d over dt of j hat over here? Well, let's look at them. So I hat is a unit vector, right? What is this unit vector? It's over here, and j hat is the other unit vector. Unit vectors by definition are the vectors that have unit magnitude. Their magnitude is 1, and that magnitude remains 1 always with time, right? So the magnitude part of I hat and j hat is really not changing. Okay, now let's talk about the direction of I hat. So is the direction of I hat changing or the direction of j hat changing? No, that is not changing either, because whether the particle p is here or over here at p prime, your I hat and j hat are always pointing that way, right? This is I, this is j, your I hat is this way, j hat is this way. So neither the magnitude nor the direction of the vector I hat and j hat are changing, which means that both of these quantities are actually zero. And that's why velocity actually reduces to dx over dt I hat plus dy over dt j hat. Okay, and in short, now onward we will write dx over dt, which is the differentiation with respect to time, as x dot right on top. So a dot on top of a variable indicates its derivative with respect to time. Okay, if I put two dots, so dx over dt is x dot. If I put two dots, that means second derivative, so d2x over dt2. If I put three dots, which we will not see in this class, that would mean d3x over dt3. Okay, so that's a shorthand. So this becomes x dot I hat plus y dot j hat, and that's the velocity. Okay, now what about acceleration? Acceleration would be x double dot I hat plus y double dot j hat. That would be the acceleration. And this was, essentially the Cartesian coordinate system that we have looked at, right? So if you knew position vector, you could get the velocity, you could get the acceleration, and the rate of change of the position vector, the unit vectors was zero, because we employed a Cartesian coordinate system in which the direction and the magnitude of the unit vectors doesn't change. But this whole thing is about to change now, because there are certain kinds of problems where employing a non-Cartesian coordinate system may be more useful. Okay, so for example, let's say I have a scenario where I am given the motion of a particle along a curved path. All right, so let's say the particle is over here, okay, right over here, and it's moving along this curved path in this direction. So it has a certain velocity v over here. It gets over here, which is p prime. It has a different velocity v prime over here. Okay, if let's say you were driving your car along this curved path, and you were constrained to drive the car at same speed. Okay, so let's say you were driving at 55 miles an hour, and that was the speed limit on the road, and you were driving along this path. Then you know that when you are passing through this section, right over here, let me draw this with a different color. So let's say if you're passing over this section, you will have a much easier time negotiating this turn. There is a little bit of turn over here versus over here. Why? Because over here, actually, you're taking, over the red trajectory, you're taking a much tighter turn than you are taking over the blue trajectory, right? So what do we mean by the tighter turn? Well, at any point on a curved path, you can actually fit a circle that will essentially be tangent to the path at a particular point. Okay, and that circle is actually called an osculating circle. So it's called osculating circle. Osculating is a Greek word, if I remember right, and which basically means kissing. Okay, so it's a kissing circle. So at point P, you have a circle that you can fit that will be essentially kissing this path or hugging this path at point P and be tangent locally at point P. Okay, and the radius of this, let's say, is given as rho, right? So that's, radius of curvature essentially over here. But at point P prime, the circle that you will fit would be much smaller, okay, and its radius of curvature is, let's say, rho prime, and clearly rho prime is smaller than rho, right? So if you have a tighter turn, which essentially means radius of curvature is actually smaller, then you feel more sideways thrust, right? So if your car was going over this section, right, you will feel more sideways thrust over here than you would feel if you were passing through this blue section. Okay, so clearly there is some sort of relationship between the acceleration or the thrust that you feel and the radius of curvature of a path at any given point, right? So now this radius of curvature information really doesn't explicitly appear when you're analyzing the motion of particles using Cartesian coordinate system, right? To analyze this kind of problem where you may be given a speed and radius of curvature, you actually employ a different kind of coordinate system. So at this point, you may be thinking, how would I know which coordinate system to use when? Well, most of the time, the problem and the information given to you in the problem will tell you sort of indirectly, it'll give you a hint what coordinate system you should employ.